In this lecture, we'll focus on how to think like an attacker so you can build stronger AI agents. The goal is to understand the main types of prompt injection and the real risks they create in production systems, from manipulated outputs to unsafe tool use and data exposure. We'll also look at the attack side through automated testing and ethical red teaming, using structured methods to uncover weaknesses before someone else does. And just as importantly, we'll cover how to defend your agents with practical best practices that improve resilience and reduce the impact of prompt injection in real-world applications. Prompt injection is one of the most important security concepts to understand when working with large language models. It happens when a malicious input overrides the model's intended instructions and changes its behavior in ways that were never meant to happen. The key issue is that the model processes system instructions and user input together as one shared context. It does not naturally enforce strong boundary between trusted instructions and untrusted text. That means an attacker can insert language such as ignore previous instructions and try to take control of the response. This is why prompt injection is considered such serious risk. It is ranked as the #1 LLM risk in OWASP LLM 2025, and it remains a problem even when techniques like retrieval augmented generation or fine-tuning are added. Those approaches can improve capability, but they do not remove the underlying vulnerability. Why does prompt injection work? The root issue is that large language models do not have true privilege separation. They process developer instructions and user input together as plain text in the same context window, so the model does not reliably know which instruction should have higher authority. That leads to authority confusion. If a malicious instruction is written in a way that sounds more direct or more important, the model may follow it even when it conflicts with the intended rules. In other words, the system can be influenced by whichever command appears most authoritative, not necessarily by where that command came from. There is also semantic blindness. Traditional security defenses are good at spotting known patterns and suspicious syntax, but prompt injection is about meaning. The attack is hidden in natural language, so standard filters and web security tools often miss it entirely. There are 4 main types of prompt injection attacks, and each one reaches the model in a different way. Direct prompt injection is the most obvious form. The attacker places malicious instructions right in the user input, trying to override the system's intended behavior. It can be easier to recognize, but it still works often enough to remain serious risk. Indirect prompt injection is more subtle. In this case, the harmful instructions are hidden inside external content such as emails, PDFs, or web pages that the AI reads as part of its task. This makes the attack much harder to notice, especially when the model is connected to tools or workflows that automatically process outside data. Jailbreak attacks focus on bypassing safety controls. Attackers use techniques like roleplay, reframing, or even multilingual prompts to push the model into ignoring restrictions and producing prohibited behavior. Cross-Plugin injection targets the tools around the model. Instead of only manipulating the AI text output, the attacker tries to influence plugin or tool usage, causing the agent to make unauthorized API calls or take actions it should never perform. The key idea is that these attacks are not all the same. They vary in visibility, delivery method, and impact, which means defending against them requires more than a single control. Chapter 1 focuses on real-world threats. The key point here is that prompt injection is no longer just a research concern or a future possibility. By 2025, it became an operational security issue with documented incidents affecting real organizations. That matters because it changes the conversation from what could happen to what is already happening in enterprise environments. Here are 4 high-impact attack scenarios that show how prompt injection becomes a real business problem. In a customer support chatbot hijack, an attacker can override the assistant's instructions, pull sensitive information from private systems, and even trigger actions like sending emails that turn simple chat interface into path for data exfiltration and privilege escalation. In RAG system exploit, single poison document can do significant damage. It can leak internal business intelligence, weaken or disable safety controls, and influence the model to make elevated API calls all through content that looks like normal uploaded data. With an AI agent worm, the risk becomes autonomous and self-propagating. Malicious prompt hidden in an email can be read by an AI assistant and summarized, forwarded, and spread to additional contacts automatically, carrying the attack with it. And in the Bing Chat system prompt leak, a student was able to extract a hidden system prompt, exposing internal instructions and revealing weaknesses in how the system was designed and protected. The key takeaway is that these attacks target both information and behavior. They don't just leak secrets, they can also change what the AI does. This is the #1 AI exploit of 2025 because it combines disclosure, execution, and scale-in. A single attack path. First, the disclosure risk is severe. One injected phrase can expose system prompts, API keys, database credentials, and even full chat histories. That means an attacker may not need to break into infrastructure directly if the model is willing to reveal what it already knows. Second, this is not just about leaking information. It can also enable access and execution. If the model is connected to tools or workflows, prompt injection can bypass intended restrictions, trigger commands, and influence business-critical actions without human review. Third, agentic amplification makes the impact much larger. Once an AI agent can use browsers, email, and APIs, a single malicious instruction can spread across systems and turn a prompt-level weakness into a full operational breach. That is why this vulnerability is ranked as OWASP LLM for 2025. It is the top LLM security issue globally, and it is also a compliance concern. Standards like ISO 42001 and regulations such as GDPR Article 32 require organizations to assess and control input manipulation risk. If those controls are missing, the security exposure and the compliance exposure increase together. Chapter 2 focuses on ethical red teaming, which means testing your own agents the way an attacker would, but in a controlled and authorized way. The goal is simple: find weaknesses before someone else does. For AI systems, this is especially important because small prompt changes can lead to unexpected behavior. Automated red teaming helps you scale that process by generating thousands of attack variations and running them safely in staging environments. That gives you a practical way to uncover weak instructions, unsafe tool access, and gaps in guardrails early when fixes are faster and less costly. In short, a strong defense starts with intentionally trying to break your own system first. Here are 3 practical tools for automated prompt injection testing at scale. Garrick is an LLM vulnerability scanner that runs structured probe sets against either hosted or local models. It's useful when you want broad, repeatable coverage and fast way to identify common injection weaknesses. Prompt Inject is focused on benchmarking injection success rates against target endpoint. You point it at chat interface or API route, feed it customizable payload files, and measure how often those attacks succeed. LangChain Safety brings red team probes directly into agent pipelines. That makes it especially helpful for testing jailbreaks, instruction overrides, and other agent-specific failure modes inside multi-step chains. Together, these tools give you a solid starting point for systematic, repeatable security testing of LLM applications. Here's a simple Python fuzzing pattern for automated prompt injection testing against an LLA endpoint. The idea is straightforward. Define small set of malicious or adversarial payloads, send each one to the model, and then inspect the response for signs of sensitive leakage. In this example, the script tries prompts that attempt to override instructions, expose the system prompt, retrieve database contents, or reveal credentials. For each payload, it generates response and checks for risky keywords like system prompt, password, or secret. If any of those appear, the script flags the result as potentially vulnerable. Otherwise, it marks the test as safe. What makes this pattern useful is how easy it is to scale. You can start with a handful of payloads, then expand to thousands of variations to improve coverage and test more edge cases. The key safety rule is critical. Run this only in isolated staging environment, never against production systems. Chapter 3 focuses on attack simulations. In this part of the course, we'll move from concepts and testing patterns into realistic examples that show how these attacks actually play out. The goal is to see the behavior clearly, understand what the model is doing under pressure, and recognize the signs of successful exploit. Here's a simple direct injection demo. First, the agent is configured with system rule that says it should never share secrets or credentials. On paper, that sounds secure. Next, normal request comes in, like summarize this email. The assistant responds as expected, and nothing looks suspicious. The attack happens when the malicious instruction is inserted into that same request. It tells the model to ignore the earlier rules, reveal the admin password, and send it to an attacker-controlled email address. If the assistant follows that injected instruction, the result is breach. The model exposes sensitive data and performs an unauthorized action. Practical way to catch this is to log outputs for phrases like ignore and to monitor outbound API calls in real time. Indirect injection is more dangerous because the malicious instruction is hidden inside data the agent trusts. In this scenario, the agent reads a customer PDF that looks legitimate but hidden white text contains a command to override rules and exfiltrate user data to a malicious site. The key problem is that the agent is not being attacked through a visible user prompt. It is being attacked through external content like a document, an email, or a web page. If the agent can read that content, access a database, and send emails on its own, then a hidden instruction can trigger real actions automatically. The worm variant makes this even worse. An infected email gets summarized by an AI assistant, and that summary carries the injection forward. When it is shared with other people, their assistants may process it too, turning each system into an accidental carrier. The curl example highlights how easy it is to simulate this kind of attack. A payload can be embedded in otherwise normal text, and if the agent treats that text as trusted context, sensitive data like API keys can be exposed. The main takeaway is simple. External data is a hidden attack surface. Every RAG document, email, and web page should be treated as potentially untrusted input. This slide maps the main entry points for prompt injection in AI system. User input is the most obvious one. Anything typed directly by a user can contain instructions designed to override your agent's intended behavior. External data is another major source. It includes documents, emails, web pages, search results, and retrieved content in RAG pipeline. Even when that data looks trustworthy, it can carry hidden or malicious instructions. Plugins and tools expand the risk further. If an agent can call up these databases, browsers, or internal services, an injected prompt may try to misuse those capabilities to access data or trigger actions. Agent memory is also part of the attack surface. If malicious content gets stored in memory, it can keep influencing future decisions long after the original input is gone. The key point is simple. Every source your agent consumes can become an injection vector. As autonomy increases, the attack surface grows, and successful exploit can have much larger impact. Chapter 4 focuses on defenses for building resilient AI agents. The key idea here is that prompt injection is not something you solve with a single filter or one protective rule. Effective defense comes from layers working together. That means making strong architectural decisions, applying controls to what the agent receives, monitoring how it behaves in production, and testing it regularly with adversarial scenarios. Resilience is really about reducing the chance of compromise and limiting the impact if something does get through. Layered security controls work best when each control addresses a different part of the risk. At the input and output level, validate and sanitize everything coming in, block suspicious patterns such as ignore, override, or unusual delimiters, and make sure responses conform to a strict output schema. At the architectural level, keep system and user prompts clearly separated with XML tags or other structured delimiters. Also use the language model for question answering and reasoning, not for directly executing commands. Privilege minimization is equally important. Agents should have only the permissions they truly need. If database or email access is not essential, do not grant it. That limits the blast radius if something goes wrong. Finally, monitoring and testing help confirm that these controls are actually working. Use real-time behavioral logging, anomaly detection, and regular red team exercises with tools like Garak and Prompt Inject on a quarterly basis. This slide brings those protections together into a defense-in-depth architecture. At the core is input sanitization. Every user input should be filtered and validated before the model processes it. That gives us the first and most immediate line of defense. The middle layer focuses on privilege and isolation. Prompt isolation, such as using XML structure, helps separate trusted instructions from user content. Minimal permissions make sure the system can only do what is absolutely necessary. The outer layer is validation and monitoring. This includes schema checks, logging, red teaming, and ongoing observation of system behavior so suspicious activity can be detected early. The key idea is that each layer acts as an independent checkpoint. If one control is bypassed, the others still help catch, contain, and reduce the impact of an attack. In practice, input sanitization starts by identifying patterns that commonly signal prompt injection. That includes override phrases like ignore, forget, or disregard, special delimiters such as system-style markers, triple hash symbols, or angle bracket sequences, and role-switching commands like you are now act as or dan mode. It's also important to catch encoded or disguised versions of these attacks. Malicious instructions may be hidden in bizarre encoding or even multilingual obfuscation to avoid simple keyword filters. Strong implementation doesn't just block suspicious text, it also isolates user input structurally. In this example, XML tagging separates trusted system instructions from untrusted user content, making it much harder for user input to be interpreted as control logic. For additional protection, you can add secondary LLM classifier before processing. Its job is to score incoming content for injection likelihood, so risky inputs can be rejected, sanitized further, or routed for review. Standards and compliance help turn prompt injection defense into a formal security requirement, not just a best practice. GDPR Article 32 sets the expectation that organizations use appropriate technical and organizational measures to protect data in the context of AI. That includes guarding against unauthorized access that could happen through manipulation of model inputs. ISO 42001 adds structure by requiring documented risk assessments for AI input manipulation. That means organizations should evaluate these risks explicitly, test for adversarial behavior, and define mitigations as part of their AI management system. The OWASP LLM Top 10 is a practical reference point for current LLM security risks. Because this space changes quickly, it should be treated as a living standard that teams review continuously as models, tools, and agentic patterns evolve. Chapter 5 is where we turn awareness into action. The focus now is practical execution, taking the risks, controls, and standards we've covered and translating them into concrete steps your team can apply. This section is about building security posture that is measurable, repeatable, and ready for real-world AI systems. This slide gives you a quick way to assess your current security posture. For many teams, the starting point is pretty common. No automated testing, overly broad agent permissions, no clear prompt separation, and no behavioral monitoring in place. That combination creates unnecessary exposure because issues can go undetected until something goes wrong. The target state is much stronger and much more intentional. You want weekly automated red teaming to catch weaknesses early. You want minimal privilege by design so agents only have access to what they truly need. You want XML tag prompt isolation to clearly separate trusted instructions from untrusted content. And you want real-time anomaly detection so unusual behavior can be identified as it happens. The key message here is simple. Move from reactive security to built-in security, where testing, isolation, least privilege, and monitoring are part of the system from the start. This 30-day action plan turns strategy into execution. In week 1, inventory every AI agent you have and audit each one for both direct and indirect prompt injection paths. At the same time, identify every external data source those agents consume, because untrusted content is often where the risk begins. In week 2, run a baseline vulnerability scan with Garak. The goal here is to create a measurable starting point, capture the findings clearly, and group them by severity so your team knows what to fix first. In week 3, put core defenses in place. That includes input sanitization, prompt isolation, least privilege access, and output validation. These controls work best as a set, not as standalone fixes. In week 4, make the process sustainable. Train your team on ethical red teaming, define a quarterly testing cycle, and assign clear ownership so security improvements don't stall. The key idea is simple. There is no single fix. Strong AI security comes from continuous improvement, regular testing, and staying aligned with current OWASP LLM guidance. Here are the key takeaways from this topic. First, prompt injection remains the number one AI threat. It leads the OWASP list because it is practical, common, and already being used against real systems through both direct prompts and indirect content sources. Second, attack coverage needs to be automated. Manual testing is useful, but it does not scale well enough for modern AI systems. Tools like Garak and Prompt Inject help you test large numbers of variations quickly and more systematically. Third, effective defense comes from depth, not from one control. You need multiple layers working together, including safer input handling, isolation in the architecture, least privilege, and ongoing monitoring. If one layer fails, the others still reduce risk. And finally, the mindset matters. If you are not testing your systems the way an attacker would, you are leaving blind spots in place. The strongest teams are the ones that proactively probe, validate, and improve their defenses before a real attack does it for them. Hack your agents before they hack you. The reality is that the tools, techniques, and threat knowledge are available to everyone, including attackers. What makes the difference is whether your team takes action early and tests proactively, or waits until a real incident exposes the gaps. To help you put this into practice, there is testing repository with scripts, payloads, and Garak configurations that you can use in staging environment. The goal is to make it easier to start validating your agents with realistic attack scenarios. This is also a good point for questions and discussion. Bring your agent architectures, your threat models, and the edge cases you're concerned about so you can translate these ideas into your own environment.